awesome power of explosives. Violent forces that shape our world in war, peace, and terror. For 1,000 years, we've embraced the sinister alchemy of explosives with just one purpose: to create ever bigger bangs. From the earliest discovery of gunpowder, through the development of deadly high explosives, to this, the legacy of Los Alamos, the atomic bomb. Now we conduct extreme experiments and witness dramatic demonstrations to venture into the heart of an explosion. And we discover how explosives have influenced our past and promise to shape our future. The crude power of gunpowder, the lethal force of high explosives, the total annihilation wrought by the nuclear bomb. Deadly milestones in our 1,000-year quest to create ever bigger, more efficient bangs. But the bigger the bang, the harder it is to control. Scientists seek to get the balance right with the perfect fusion of destructive force, precision, and stability. Their mission takes us to the billionths of a second at the very heart of an explosion, and to some of the most volatile chemistry and extreme physics known to science. We witness what happens when terrorists hijack explosive power and glimpse a future that sounds more like science fiction than fact, where bizarre antimatter technology could deliver the biggest ever bang. But first, we must go back to basics to ask, what is an explosion? A chemical or nuclear reaction causes a fuel to suddenly and violently release energy. It expands rapidly and can produce immensely high temperatures. But all this takes place in just a fraction of a second. To understand what happens in that moment, we need to slow the process down and look into the heart of an explosion. And for that, we visit explosive expert Stephen Miller. Miller believes explosive science is best understood when taken out of the lab. Today, at his range deep in the English countryside, Miller is doing what he does best: blowing things up. He uses powerful explosives to demonstrate what it is that makes them so volatile and destructive. All explosive material burns very quickly, releasing huge masses of gas in a relatively short amount of time. During an explosion, that concentrated gas expands rapidly to fill the available space, then keeps on expanding. That ever-expanding gas cloud applies overwhelming pressure against anything caught in its way.
At the heart of an explosion, there is the rapid release of gas. It's this pushing on the local environment that destroys anything in its path. It could be cars, buildings, whatever.
This is the principle of all explosions, from the very large to the very small. All explosions require three elements: fuel, oxygen, and a means of ignition. To demonstrate what happens when these three things are brought together, Miller creates a controlled small explosion using baking flour as a fuel.
We have oxygen supply coming in through the tube here, fuel in front of it, and our ignition source. And what should happen is it should launch the tin up a few inches with lots of flames coming out.
Miller lets oxygen into the tin can. The flame ignites the flammable cloud of oxygen and flour. As the flame rapidly moves through the cloud, there is a sudden increase in pressure. The result? An explosion. But it takes a lot of energy and effort to make this relatively small bang. The proportions of oxygen and fuel must be perfect. Too little of either, and there will be no explosion. When it comes to waging war, soldiers need something more dependable. Gunpowder, the earliest recorded explosive and the god of war for hundreds of years. Gunpowder brings together the fuel and the oxygen in one neat chemical package. This modern sample contains 75% potassium nitrate, containing the oxygen molecules, 10% sulfur, and 15% carbon, in this case, wood charcoal.
Charcoal is the fuel, the potassium nitrate provides the oxygen, and the sulfur just helps it burn that bit better.
Miller ignites the gunpowder.
Firing now.
The oxygen from the nitrate enables the sulfur and carbon to burn rapidly, forming a mixture of hot gases and a sharp increase in volume. Put gunpowder in a confined space, and the results are even more dramatic. Miller fills a bottle with half an ounce of gunpowder and places it inside a wooden hut. When the gunpowder explodes, it will release heat and gas. These will build up, increasing the pressure inside the bottle. With nowhere else to go, the gases will expand outward, ripping the bottle apart. We know we can increase gunpowder's deadly force. Now, if we can direct that force, we can propel objects through the air. Objects such as bullets. Confine gunpowder within a metal barrel, add a projectile, and pull the trigger. The powder ignites. The barrel channels the expanding gases, which push the bullet faster than the speed of sound. Over centuries, this simple black powder shapes the course of history. But gunpowder is dirty. Smoke chokes the battlefield and fouls weapons after just a few firings.
Gunpowder is a perfectly good explosive. Unfortunately, gunpowder is also very dirty in burning. Up to 70% of the original mass is still left as solids in the smoke.
In the quest for an ever bigger bang, gunpowder is about to be joined by a new and terrifying explosive. This is trinitrotoluene, invented as the shadow of war looms across 19th century Europe. It's the world's first modern military explosive, and otherwise known as TNT. Unlike gunpowder, it's more than just a mixture of fuel and oxygen. TNT bonds those two essential components together within its molecules. It's a high explosive, which means the only way to release the explosive energy locked within is to shock it. And to do that, Miller must use a detonator.
With high explosives, we have both the fuel and the oxidizer at the molecular level. When the detonator goes off, the shockwave from that breaks these bonds, releasing a massive amount of energy.
The elements nitrogen, hydrogen, carbon, and oxygen make up TNT. Hit these with a shockwave from a detonator, and the molecules rip apart. Miller triggers the detonator.
Stand by for firing. Firing now.
A series of tiny charges propels a shockwave into the TNT, which detonates at a rate of 22,000 feet per second, generating pressures of over 4,000 pounds per square inch. Oxygen atoms hit by the shockwave bond with carbon and hydrogen atoms. The nitrogen atoms are released as gas. In a fraction of a second, the solid TNT transforms into a cloud of gas. It expands outward in a powerful explosion.
As we saw on the high-speed camera, even at 1,000 pictures a second, it's very difficult to capture the moment of explosion with TNT. That's because it's going off at 20,000 feet per second.
TNT is faster, bigger, and more efficient than gunpowder. To demonstrate, Miller loads a shotgun with a specially designed cartridge containing TNT.
Stand by for firing. Firing now.
The molecular structure of the TNT rips apart so quickly that the steel barrel of the shotgun cannot contain it. The immense pressure of the expanding gas blows the chamber to smithereens.
And that's why you use a low explosive propellant instead of a high explosive in guns.
But despite its immense power, TNT is far more stable than gunpowder. To prove it, we put it to the ultimate test. A marksman will fire a high-velocity bullet at 1 pound of TNT. From 100 yards away, the bullet will travel at approximately 2,045 miles per hour. But Miller is confident that the TNT won't explode. Our high-speed cameras reveal the moment of impact. The TNT disintegrates in a cloud of dust, but there's no explosion. 1 pound of TNT is 10 times more powerful than 1 pound of gunpowder. It's also more stable, cleaner, safer to store, and easier to transport. And it normally only detonates when you want it to. High explosives like TNT revolutionize the art of blowing things up. For centuries, scientists and soldiers have battled to control the lethal force of explosives, to balance power with stability. But they aren't the only people in search of a bigger bang, and some are less scrupulous. Now our journey takes us into a dark and dangerous world in which safety and stability matter less than maximum carnage. We're about to enter the world of terror. Tel Aviv, London, Baghdad. In today's world, the most destructive explosive device is often the crudest. Known as an IED, or improvised explosive device, such homemade bombs are the favorite weapon in the terrorists' arsenal. They're responsible for the majority of US deaths in Iraq. And it was an IED that caused the biggest domestic terrorist attack in the United States, Oklahoma City. IEDs are powerful, lethal, and dangerously unpredictable. The Energetic Materials Research and Testing Center in New Mexico. Its mission? To understand how these brutal devices work and stay one step ahead of the terrorists. And few people have a better understanding of IEDs than former bomb squad tech Jerry Little.
The term IED means improvised explosive devices. That is a device that has been constructed specifically for the purpose to kill. They are made by unconventional means, sometimes using conventional explosives, sometimes using improvised explosives.
The challenge for Little's experts is to understand how explosives behave from something that is more realistic than a Hollywood blockbuster.
People base what they know on explosions and explosives to what they've seen on television or it comes out of Hollywood, and that's not reality. However, when they come here, they truly learn, what the full spectrum of hazards are and how they can protect themselves and the public.
At the test range, Little's team studies the type of homemade explosive devices that may threaten the US. And the best way to do it is to blow stuff up. Lots of stuff. 400 pounds of improvised explosive destroys a prefabricated building. A rudimentary letter bomb delivers some bad news.
It's missing most of the head, and both shoulders and arms are outside the door.
A pipe bomb annihilates a watermelon. The shrapnel spread by the blast lacerates the fruit, copying the effects of bomb fragmentation on human flesh. A wooden dummy wearing 3 pounds of plastic explosive detonates, replicating the carnage created by a suicide bomber. Today, it's the turn of this car. In the trunk, there is enough explosive to blow a building apart. The car bomb is the device of choice for terrorists both at home and abroad. Vice President of the facility and explosive expert Van Romero believes this type of study is critical for Homeland Security.
After the 9/11 event, the expertise that exists here came to the forefront. There was really something that we could do to help the country protect itself against terrorism.
The car bomb IED is made from ammonium nitrate, an agricultural fertilizer, and nitromethane, a highly volatile auto racing fuel. Shrapnel may blast thousands of feet, so everyone on the site must take shelter in a bunker 2,500 feet away. Mirrors allow the course participants to view the explosion in safety.
All right, we're ready for our first set of shots for today. 1994 Pontiac Sunbird. Don't blink, this is all gonna happen once. Stand by for count. 5, 4, 3, 2, 1. Gosh.
Chemical explosions like this produce a powerful shock wave. It tears through the explosive and out into the environment. At the moment of detonation, the explosive expands. A massive volume of air moves outward. It's this phenomenon that creates the shock wave. The shock wave moves at supersonic speed. It forces moisture in the air to condense instantly. This creates a sudden white cloud or flash. It's why you see an explosion, but hear the bang seconds later.
The chemical reaction is causing a shock front that's radiating out from the center or the seat of the detonation.
High-speed footage gives us a unique glimpse of the shock wave as it moves across the desert floor and rises above the New Mexico skyline. The shock wave travels at over 1,220 miles an hour, about 1.5 times the speed of sound.
That shock wave travels through the air and can do damage to buildings, to human beings, to the environment.
The shock wave exerts a blast pressure of up to 5,000 pounds per square inch, the equivalent of 10 2-ton trucks hitting a wall at 175 miles per hour.
If you get 10 to 15 psi, you start destroying your eardrums. A few psi could knock you down. 20 or 30 psi would damage a building.
The blast wave rushes out from the explosion, pushing everything out of its path. In its wake, it leaves a void. Negative pressure builds up, sucking the air backward toward the site of the explosion.
So sometimes in a building, you may see, if a device has exploded inside of a building, you'll see glass that gets pushed out and then sucked back into the building because of the negative effect of the shockwave.
Just on the outskirts here, we have part of a wall from the building. How did that wall from the building get back here? That negative pressure with that air rushing back in took some of that building and just sucked it back in here.
The blast propels debris from the explosion. Jagged scraps of shrapnel rip through the air like bullets.
Another hazard that we're really concerned with is the shrapnel fragmentation effect. That is, objects, either part of the device, things that have been added to increase lethality, or things that are in close proximity that are being propelled by the force of the detonation. Typically on the car bombs with 500 pounds of explosives, we get fragmentation shrapnel that travels anywhere between 1,700 to probably 1,900 feet.
Find yourself near an IED like this, and shrapnel could cut you down even 1,800 feet from the blast. That's as far as 6 football fields laid end to end. And if the initial blast doesn't kill you, the after effects could. The bigger the bang, the more it will damage or destroy nearby buildings, turning them into death traps for the people inside and the first responders sent to rescue them. If scientists can understand the incredible power unleashed by a terrorist explosion, they could begin to build safer buildings. But there's one overwhelming problem: fire. It masks much of the damage caused by an explosion. So at the University of California, San Diego, Professor Gil Hegemeyer came up with an ingenious way to look into the heart of an explosion without ever having to blow something up. This blast simulator delivers the same knockout punch as a car bomb. It uses rubber-coated steel plates powered by hydraulic pistons to smash into buildings, and creates the effects of a terrorist explosion without the resulting fireball.
This is the highest speed hydraulics you'll find in the world, okay? There's nothing probably in the universe.
With no fireball, high-speed cameras and instruments can record what happens close up.
You have a fireball, you can't see anything, typically, and the debris field plus the fireball will take all your instruments and do nasty things to them.
In a bomb blast, the pressure blasting against the building structure creates the most devastation, not the ensuing fireball.
The pressure pulse delivered to the specimen is what's important here. This machine does produce the knockout punch that you get from a real explosion. It delivers all the energy to the specimen that it would see from an actual charge going off, such as a car bomb at the curb.
Today, Hegemeyer studies a new technique to protect buildings against terrorist attacks. He wraps a column in a special polymer to see if it can withstand the equivalent force of a car bomb blast. This industrial wallpaper, known as reinforced polymer, is as thin as a cotton shirt, stronger than steel, and consists of carbon threads bonded with resin.
When you wrap, you contain and confine the concrete and prevent those fragments from moving through a building and killing the occupants.
In the accumulator bank, pressure builds. Outside, this pressure is about to be released. Generators drive steel plates precisely shaped to replicate an explosion shockwave as it pulverizes the concrete.
6, 5, 4, 3, 2, 1. Fire. We are at high pressure.
Right now, that column is under 100,000 pounds of vertical force. So if that was a column in a real building, it's still good to go. It may not look so good, but it's supporting the load, and that's what those carbon wraps are all about.
The carbon fiber wrap protects and supports the column. An unwrapped column is blown to pieces. This technology has huge implications. It could have saved many lives in Oklahoma City during the 1995 terror attack that destroyed the Alfred P. Murrah Federal Building.
The structural collapse took more lives than the actual blast effects. One column that could no longer support its load initiated a catastrophic failure sequence.
But for all the savagery of terrorist bombs, they're unstable, unpredictable, and inefficient. They're as likely to kill the bomber as their intended target. Sometimes they fail to detonate altogether. In the quest for a bigger bang, this lack of precision gives scientists a winning advantage. Because unlike the terrorists, they have the technology and expertise to develop explosives that are powerful and stable. It's a delicate balance. To get it right, scientists must investigate events that take place in just a few billionths of a second. They must penetrate the very heart of an explosion. From the battlefield to our cities, we're seeing the awesome power of explosives and witnessing their terrible consequences. In the art of blowing things up, we've come a long way. Today's high explosives are about 15 to 20 times more powerful than gunpowder. But with more power comes less control. And unless a bomb goes off when you want it to, it's worse than useless. The task of balancing a bigger bang with increased stability falls to Dr. Randall Simpson at the Lawrence Livermore National Laboratory in California.
All of these materials need to be stable. That is that if they're unstable, they're of no value for civilian use or for military use. The goals for national security missions or industrial use are materials that are so stable that they will not explode in a fire environment. Another requirement is they last for a very, very long period of time.
To create safe and stable explosives, Simpson and his team analyze the events that occur at the heart of an explosion. Here, complex chemical reactions take place in just a few billionths of a second, and temperatures can reach 9,440 degrees Fahrenheit.
We refer to this type of chemistry as extreme chemistry, chemistry that occurs up to 500,000 atmospheres of pressure. Chemistry that occurs up to several thousand centigrades, chemistry that may occur on very, very short time frames. All of those extreme conditions are represented by the detonation of an explosive.
This is extreme chemistry, conducted at a molecular level.
When you're working with hazardous materials, you start off with very small quantities until you understand the properties, and then you gradually increase the quantities of materials that you work with.
Today, they are testing one of the most advanced high explosives in military use, LX-14. It's an extremely powerful plastic-bonded high explosive. 1 teaspoon of LX-14 is about 17 times more powerful than a teaspoon of gunpowder. It's used to detonate missile warheads. The team are carrying out a series of tests to examine how LX-14 behaves at the moment of detonation.
And here comes the fire. Go reaction.
By studying the mechanics of each blast, they can design explosives that deliver the required bang, but with the necessary stability. They bind the explosive material in plastic. The plastic absorbs shock, reducing the risk of accidental detonation. The trick is to create a complex cocktail of explosive material and plastic polymer that will detonate with the required force, but only when triggered.
There are misconceptions about explosives that they're chaotic, they're very random, but if done properly, they can be extraordinarily precise and safe materials to work with.
This is LX-17. It's more stable than LX-14, but less powerful. It's used in warheads and only explodes if detonated by a more powerful explosive, like LX-14. It's so stable, it's even possible to machine it, turning the high explosive into three-dimensional shapes for use in weapons. It can even survive a plane crash without detonating. John Molitoris studies the power and stability of explosives by analyzing the shock waves generated by a controlled detonation.
The problem is you make an HE more insensitive. What you do is you make it less powerful. The real trick is to make the high explosive more insensitive, but also give it the same explosive power, which is the name of the game.
The test takes place in these huge containment tanks. They can absorb immense heat and pressure and survive a blast of up to 22 pounds of high explosive.
The violence of these reactions can vary enormously. Metal will fly at 2 miles per second.
Molitoris measures the temperature of the fireball as it grows and expands using a pyrometer.
As the fireball grows, these things will measure the very violent changes in pressure and temperature.
He also measures the impact of the shock wave on the metal holder containing the explosive. Safe behind bomb-proof doors, technicians record the precise moment that the explosive detonates.
3, 2, 1, trigger.
Wow. That's fantastic. Look at that. That's great. It's really great.
Tank is venting.
The destructive power of the explosion surprises even Molitoris.
I didn't think that type of high explosive in that geometry would fragment it to that degree. I thought there'd be some little plate left over. A little bit confounded about that.
The explosive tears apart the half-inch thick aluminum holder on which it is sitting. To do this takes less than 5 ounces of LX-14. Imagine what a warhead containing 2,000 pounds of it could do.
It is a pretty powerful high explosive, and that's the nature of the game. That's why we do experiments. You know, you don't always know what you're going to get.
They use the data from experiments like these to build sophisticated computer models. These can predict the relative power and stability of an almost infinite number of chemical combinations. For the Livermore team, the test is part of a never-ending mission to balance power with stability, to create explosives with just the right bang, that explode at just the right time. But in the quest for an ever bigger bang, this is just the beginning. These powerful chemical reactions are nothing compared to the forces that physics can unleash. Now, we prepare to enter the atomic age and witness the biggest ever man-made explosion. For centuries, scientists combined chemicals to create ever bigger bangs. Now, we witness what happens when they take the world apart and unleash the extraordinary energy contained within the fabric of the universe itself, the atom. The scorching New Mexico desert, a vast wilderness. July 16th, 1945. It's teeming with activity. This is the Trinity test site. Here, a new and terrifying age is about to dawn. 5:29 a.m. The world's first atomic bomb detonates with the force of 20,000 tons of high explosive. 10 miles away, observers feel the explosion's heat on their skin. The flash is brighter than 20 suns. It's the biggest man-made explosion to date. The world will never be the same again. But the biggest bang is produced by a chain reaction of tiny particles. And none of it would happen without conventional high explosives. John Rhodes is the director of the Bradbury Science Museum at Los Alamos, New Mexico.
Today we think of our contemporary nuclear weapons as the absolute zenith of destructive power, but they can trace their roots back to low energy gunpowder, which then over time became high energy, high explosives.
The long line of explosives, from gunpowder to TNT, leads to this, Little Boy. 28 inches in diameter, 10 feet long, Little Boy is a small package designed to deliver an explosive force equivalent to 15,000 tons of TNT. Inside are two masses of a heavy metal called uranium, a target and a bullet. Kept separate, there's not enough uranium in one place to sustain a chain reaction. The bomb is said to be subcritical. Conventional high explosive fires the bullet at the target, bringing the two uranium masses together. The bomb becomes critical. Now, there are enough neutrons bombarding the unstable uranium atoms to initiate a devastating release of energy. This is the principle of a fission bomb. The uranium nucleus accepts a neutron. It splits into smaller atoms and more neutrons. These neutrons proceed to split other uranium atoms. It's a chain reaction. Each reaction releases a vast amount of energy in a very short time. The gathering energy blows the bomb apart with a massive blast. It all happens in a split second at 8:15 a.m. on August 6, 1945, 1,900 feet above the Japanese city of Hiroshima.
This is the uranium weapon that was used on Hiroshima. It starts with the detonation of conventional high explosive to fire the shell against a uranium target. Subcritical, critical, boom.
In that moment, the bomb kills 70,000 people and injures as many again. Many more die as a result of radiation sickness. And Little Boy has a big brother. Los Alamos scientists have developed another bomb.
And they wanted to bring into its use plutonium, which had just recently been discovered, which was more energetic, basically more bang.
This is Fat Man. Unlike the gun-type device of Little Boy, Fat Man uses implosion to compress the subcritical assembly of another unstable metal, plutonium.
The idea is you take a core of plutonium, you surround it with a jacket of high explosives, and you detonate it.
3 days after Little Boy delivered its deadly cargo, Fat Man explodes with the equivalent of 21,000 tons of TNT above the city of Nagasaki. But whatever the method of detonation, the terrifying effects of an atomic bomb remain the same. An instant after detonation, a fireball, a luminous mass of air, starts to expand. Even from 50 miles away, a nuclear blast is many times brighter than the midday sun. Looking directly at the blast could destroy your light receptor cells, permanently burning a large spot into your retinas. A massive blast wave surges outward, destroying everything in its path for mile upon mile. Approximately half of the energy goes in blast, about a third in heat, and the rest in radiation.
The first and most obvious is blast. There's a tremendous shock wave that's propagated outwards from ground zero where that weapon is detonated. A shock wave that can take down buildings, can move vehicles, can twist railroad tracks. You not only have blast, but you've got heat approximating near the temperature of the sun. so that anything around is immediately vaporized, immediately incinerated.
The fireball increases in size and cools. The vapors condense to form a cloud containing solid particles of the weapon debris and small drops of water sucked into the fireball from the air. Nitrous acid and oxides of nitrogen make the cloud appear red or brown. As it cools, the water droplets condense, changing it to white, just like an ordinary cloud. But the contents are far from ordinary. The cloud is full of deadly radioactive particles. As they blow downwind, they fall to the ground and contaminate thousands of square miles. Find yourself in the contaminated zone, and you could be exposed to a lethal dose of radiation. A low dose will damage your cells, but your body should repair itself. A higher dose may overwhelm your body.
The effect of radiation on the human body in these extraordinary doses is really only known from Hiroshima and Nagasaki. It has the ability both to penetrate and to do extraordinary cellular damage, as well as serious burning to any exposed part and internally.
But despite its countless horrors, the nuclear genie is out of the bottle. Now the Cold War superpowers race to stockpile ever more powerful nuclear weapons. November 1st, 1952. U.S. government scientists in the Marshall Islands press the button that ushers in a new era of explosive power. The age of the H-bomb. This bomb is 1,000 times more powerful than the atomic fission bombs that fell on Hiroshima and Nagasaki. Unlike those bombs, which created energy by splitting nuclei in a process called fission, this new weapon forces the nuclei of hydrogen atoms together. This is nuclear fusion. High explosive first initiates a fission reaction. This creates super high temperatures. In the intense heat, the hydrogen nuclei fuse to form helium. This releases a huge amount of energy and creates a massive explosion.
When you get to fusion, all bets are off. And really, there is almost no upper limit.
Thanks to the H-bomb, the U.S. leads the arms race, but not for long. October 30th, 1961, a Soviet bomber flies toward a remote island in the Arctic Circle. On board, a special cargo, a 27-ton hydrogen bomb. This is the king of bombs, the Tsar bomb. At 8:33 a.m. Greenwich Mean Time, the Soviet Union sets a new and terrifying record. The Tsar bomb explodes with 3,800 times more power than the Hiroshima bomb. The fireball is seen over 600 miles away. Shockwaves circle the Earth 3 times. This is the greatest man-made explosion in human history. It heralds an age of mutually assured destruction, in which there are enough nuclear bombs to destroy humanity many times over. It's a threat which, despite countless treaties and agreements, continues to this day. This is the ultimate bang. In the space of 1,000 years, explosive power increases hundreds of millions of times. But nuclear bombs are dirty and indiscriminate. They render the land on which they fall useless, and their deadly legacy can last for thousands of years. So the quest for a bigger, better bang continues. And in the fallout from the atomic age, scientists think they may have found the key to the ultimate bang, to an explosion of immense power and precision. We're seeing the awesome power of explosives, from the crude force of gunpowder to the biggest ever bang. Now it's possible conventional explosions such as these could become a thing of the past. The future promises explosive devices of unprecedented power. In their search for the biggest bang of all, scientists are now experimenting with the most powerful energy source known: antimatter. It sounds more like science fiction than fact, but antimatter is real. Physicists have known about it since the 1930s. In theory, 1 ounce of antimatter could replicate the power of 75 Hiroshima bombs. Antimatter forms naturally in rare ultra-high-speed collisions, such as those that happen inside solar flares. But now, scientists can produce antimatter on Earth. A particle accelerator sends atoms smashing into each other at near the speed of light. The collision produces antimatter, the opposite of matter. And when antimatter and matter collide, they annihilate each other. Energy locked within the particles is released in a billionth of a second. The reaction produces nothing but pure energy. It's nearly 1,000 times more efficient than a hydrogen bomb, 40 billion times more efficient than TNT. Imagine the power of a weapon which weighs as much as a paperclip and could destroy a city the size of New York. It's a nightmarish vision straight out of a science fiction movie, which is where physicist Professor Richard Thompson thinks it will stay.
Realistically, the amounts of antimatter that have ever been made or could be made realistically in the future is very, very small. And the process by which you generate it is extremely inefficient. It takes enormous amounts of energy and enormous amounts of time to generate any significant amount of antimatter. And to accumulate any significant amount of material that you could weigh would take billions of years.
And keeping hold of it is even harder. The usual way to contain antimatter is in an airtight metal tube called a penning trap. Antimatter particles aren't visible to the naked eye. This trap demonstrates the principle on an enlarged scale. Inside, powerful electromagnetic fields would constrain the antimatter. A similar magnetic force inside this desktop toy keeps the globe suspended.
So the globe is now suspended by those forces, and because of that, it doesn't fall, it doesn't touch the base, it doesn't touch the sides, and that means that if it was an antiparticle, then it wouldn't be touching the apparatus at all.
But if the antiparticle did touch the matter in the walls of the trap, it would annihilate on contact.
The amount of matter that you can put into one of these traps is very limited. The reason for that is that because these are charged particles, they all push away from each other, and that means that the density that you can get within the trap is very limited. The explosive power of that, if you were to convert it entirely into energy, would be just a tiny fraction of the energy that's contained in a match head.
It seems that antimatter, the ultimate destructive material, must remain in the realm of science fiction for now. The never-ending quest for a bigger, better bang. Of all the world's technologies, few have experienced such a rapid rate of progress. From gunpowder and lethal high explosives to savage terrorist devices and the awesome annihilation of the nuclear bomb. In the space of just 300 years, explosive power has increased more than 100 million times. Now we stand on the threshold of a new explosive age, as scientists push the boundaries of possibility even further in search of an ever bigger bang.